All right, welcome back to DevOps Corner. Today, we're going to do something a little different. We are going to build a complete modern tech stack right from the ground up. And look, we're not just going to list a bunch of tools, we're going to architect a real system piece by piece so you can see how all of this actually connects in the real world. We'll follow the logical progression of problems that every single growing software project runs into, and we'll see which practices and tools pop up to solve them. By the end of this, you'll see the entire journey, from a single line of code to a fully operational, scalable, and observable system in the cloud. Let's get into it.
Everything, and I mean every application, every website, every piece of software you use, it all begins right here. It's just a developer, an idea, and that very first line of code. This is the spark. But you know what? The second a second line of code is written or a second developer joins the team, we hit our very first fundamental problem. And it has nothing to do with the code itself, it has everything to do with people working together.
But hold on. Before we even tackle that first problem, we have to talk about the ground we're all standing on. You can't build a skyscraper on sand, right? In our world, the absolute bedrock is this trifecta right here. You've got Linux and the command line because, let's be real, the vast majority of servers and, more importantly, all the containers we're going to talk about, they're built on the Linux kernel. Then you have networking basics, because our apps are distributed systems that live and die by talking to each other over HTTP. And finally, scripting, because automation is the heart and soul of DevOps. Without a solid grip on these, none of the fancy tools we're about to dive into will make a lick of sense. This is the language of our infrastructure.
Okay, so back to that first big problem. You've written some amazing code. Your teammate, who's working from home, has also written some amazing code for a different feature. So, how do you merge them? What happens if your change accidentally breaks their change? And how in the world do you go back to the version from last Tuesday that you know worked, right before someone introduced that critical bug? I think we've all seen it. Emailing zip files named project_final_v3, I swear this is final.zip. It's a recipe for absolute disaster. We need a system, a single source of truth.
And that system is Git. Now, Git is so much more than just a tool, it's the entire foundation of modern collaborative software development. It was famously created by Linus Torvalds to manage the development of the Linux kernel itself. I mean, think about it. One of the most complex software projects in history with thousands of contributors. That's the scale of the problem it was built to solve. Git lets us create these isolated branches to work on new features without messing up the main codebase. It tracks every single change with a permanent record, and crucially, it lets us rewind time if something goes wrong. Think of it as the ultimate shared undo button for your whole team. It's the first critical step from being a solo coder to being a professional engineering team.
So, our team is in a good rhythm now, right? They're using Git to manage their code. But a new, much more sneaky bottleneck starts to appear. Every time a developer wants to get a change out to users, some poor soul has to perform this manual ritual. They have to pull the latest code, compile it, run a bunch of tests by hand, and then carefully, so carefully, copy the files over to a server. This whole process isn't just painfully slow, we're talking hours, sometimes days, but it is dangerously prone to human error. I mean, imagine a late-night deployment where a single config value is missed. The whole system can come crashing down. This is the wall where developer productivity goes to die.
We break through that wall with automation. This is where we introduce the CI/CD pipeline, and we'll start with the first half, continuous integration, or CI. The idea is simple, but it is absolutely revolutionary. The second a developer pushes a code change to Git, a machine automatically takes over. It runs the build process, compiles the code, packages it all up, and more importantly, it runs our entire suite of automated tests, unit tests, integration tests, you name it. If a single one of those tests fails, the developer gets an alert almost instantly. The feedback loop shrinks from days to minutes. They know right away if their change broke something, while the code is still fresh in their mind.
And this right here, this is where we see the first massive payoff for the business. The impact goes way beyond just code. This quote just nails it. When that feedback loop is this fast, developers can fix critical bugs in minutes, not weeks. They can ship new features without getting stuck in bureaucratic change request meetings and manual deployment checklists. This is what people mean when they talk about developer velocity. The business moves faster, customers get value sooner, and honestly, developers are way happier because they're spending their time solving cool problems, not wrestling with broken deployment scripts.
Ah, yes. The 6 most infamous and frustrating words in all of software development. Our automated pipeline is glowing green, all tests passed with flying colors. We deploy to production, and it blows up.
The developer is completely stunned, and you hear them say, "But it worked on my machine." Look, this isn't just an excuse. It's a symptom of a really deep problem. The developer's laptop has a slightly different version of a library than the CI server, which has a different OS patch level than the production servers. These tiny, invisible differences in the environment create absolute, unpredictable chaos.
We solved this problem with containerization, and the undisputed king of containerization is Docker. A Docker container is basically a standardized shipping container, but for our software. We don't just ship the code anymore. We package the code, the runtime like Python or Node.js, all the system libraries, and every single configuration file into a single, sealed, immutable box. This box, this container, is a perfect snapshot of a working environment. And here's the magic part. That box will run identically, bit for bit, anywhere that Docker is installed. On a developer's Mac, on the CI server, and in production. The works on my machine problem, it's gone, for good.
So we've solved for consistency. Awesome. But this is where things get really interesting. Because now we have to talk about scale. Our application is a hit. We're getting more and more users. A single container on a single server just isn't going to cut it anymore. For a small feature launch, maybe we need 10. For the holiday shopping season, we need 100. For a massive Black Friday event, we might need 1,000 containers spread across dozens of physical servers. How do you manage all that? How do you update them all without any downtime? And what happens if one of them just crashes at 3 a.m.? You can't manage this storm manually. You need an orchestrator. And that orchestrator is Kubernetes. If Docker gives us the standard shipping container, then Kubernetes gives us the entire automated shipping port, the cranes, the ships, the global logistics network to manage all those containers at a massive scale. We stop thinking about individual servers. Instead, we just describe our desired state to Kubernetes. We say, hey, I need 10 copies of my web server running at all times, and they should be accessible to the public. Kubernetes handles everything else. If a server dies, Kubernetes automatically moves those containers to a healthy one. If traffic spikes, it automatically adds more containers. It handles networking, storage, self-healing. It is, for all intents and purposes, the operating system for the cloud.
So we've got our application in containers, orchestrated by Kubernetes at massive scale. But there's a big question we haven't answered yet. Where does all of this physically run? Now, historically, you'd run it on-premise, in your own data center. You had to buy the servers, rack them up, manage the power and the cooling. It was a slow, expensive process. Today, the answer is overwhelmingly the public cloud. AWS, GCP, or Azure. Instead of buying hardware, you're just renting it, on demand, paying only for what you use. You can get a new server in seconds, not weeks. This gives us the elastic foundation our Kubernetes cluster needs to truly scale up and down. By the way, if you're enjoying this systematic buildup of a modern tech stack, a quick like on the video really lets me know we're on the right track.
The cloud gives us incredible power, but with that great power comes great complexity. To run our Kubernetes cluster, we need to set up virtual networks, subnets, internet gateways, virtual machines, load balancers, databases, not to mention a whole complex web of permissions. Trying to do all of this manually by clicking through the AWS or GCP web console is just as bad as the manual deployments we automated away earlier. It's slow, it's prone to error, and worst of all, it is not repeatable. How can you be 100% sure your staging environment is an exact replica of production? You can't. This problem is called configuration drift, and it is an absolute nightmare.
We solved this with a huge paradigm shift called Infrastructure as Code, or IAC, and the dominant tool in this space is Terraform. The whole idea is to define our entire cloud infrastructure, our servers, our networks, our databases, in configuration files, just like we write application code. These files become the single source of truth for exactly what our infrastructure should look like. Now we can version control our infrastructure with Git, we can have teammates peer review changes to our firewall rules, and we can fully automate the entire provisioning process. We can spin up an identical, production-ready environment from scratch in minutes with a single command. It's reproducible, it's automated, and it's collaborative. It's a game changer.
Okay, let's just pause and take a breath for a second. Look how far we've come. Our developer's code is in Git. A CI/CD pipeline automatically builds and tests it, producing a Docker container. Kubernetes is running that container at scale on cloud infrastructure that we provisioned with Terraform. Our application is live, serving real users. We're done, right? Not even close. In so many ways, the most critical phase is just beginning. How do we know if the system is healthy? Is it fast? Is it throwing errors? Are our users actually having a good experience? Without data, we are flying completely blind.
To see inside our complex system, we need what's called observability, and it's built on these key pillars. First, logs. These are the detailed event-by-event narratives that tell us what happened, like an error on a single request.
Then you have metrics. These are just numbers over time, like CPU usage or request latency, that tell us how the system is performing at a high level. Now, traces. This is the secret sauce in a microservices world. A trace follows a single user request as it bounces between all the different services, telling us exactly why an operation is slow. And finally, you have alerting. This is where we use tools like Prometheus to watch our metrics and automatically tell us what needs our attention right now, often visualized in dashboards with Grafana, so we can fix problems before our users start complaining on Twitter. This feedback loop is what gives us the confidence to operate a complex system.
Okay, so what we've just built is the complete foundational DevOps loop. This is the core of what you absolutely need to know today. But, this field is always evolving. It's always being pushed by the need for more speed, more security, and more efficiency. So let's take a quick look at the advanced practices that are really defining the future of DevOps heading into 2026.
These advanced practices built directly on top of the foundation we just laid out. First, DevSecOps is all about shifting security left, which just means embedding automated security scans for vulnerabilities and misconfigurations right into our CI/CD pipeline, not treating security as some final checkpoint before release. Then there's GitOps. This takes infrastructure as code a step further, making a Git repository the single declarative source of truth for everything. The desired state of the entire system lives in Git, and automated agents are constantly working to make reality match what's in the repo. And finally, platform engineering. This is a big one. It's about taking all these complex tools, Kubernetes, Terraform, CI/CD, and building a simplified internal developer platform on top of them. So an application dev who just needs a new database can get one with a few clicks without needing to become a Kubernetes expert.
And there you have it. We started with just a single developer and one line of code. We solved for collaboration with Git. We solved for speed and quality with CI/CD. We solved for environmental consistency with Docker and for massive scale with Kubernetes. We ran it all on elastic cloud infrastructure that we managed with Terraform as code, and finally, we made the entire complex system observable. You see how each step solved a specific, painful problem, and each solution became the foundation for the next level of scale and complexity? This is how modern, resilient software systems are built today.
I want to end on this because it's probably the most important point of all. We've talked about a lot of really powerful tools, but DevOps is not about the tools. It's a culture. It's about breaking down those old walls that used to exist between development teams who want to move fast and operations teams who value stability above all else. It's a mindset that's focused on shared ownership, on automation, and on creating these super fast feedback loops so we can deliver value to our users more quickly and more reliably. The tools, they're just what enable that culture to thrive.
So, as you go back to your own projects, I'll just leave you with this one question. Take a hard look at your workflow. From the moment code is written to the moment it's in the cloud. Where's the friction? Where are the manual handoffs and the repetitive tasks? What is the next bottleneck that you can automate away? Because finding those things and fixing them, that's the real core of the DevOps mindset. Thank you so much for joining me on this journey. If you found this explainer helpful, please give it a like and subscribe for more deep dives into complex topics. I'll see you in the next one.